So 30 out of 40 was the average for this paper. Feels pretty high. All right, question 1. Well, they've given me the mass and the molar mass. So let's just do some moles. So I've got moles is mass over molar mass, which is going to give me 1/5 of a mole. So I've got 1/5 of a mole of ethanoic acid. So 1A would be the answer if that was the question, but that's too simple. They're asking me for the number of carbon atoms. So that's going to be a huge number. Carbon atoms are really small. It's 12 grams. There's going to be loads of them. So it has to be C or D. It has to be a big number. Well, for every 1 mole of ethanoic acid, I'm going to have 2 moles of carbon because those carbons are in that molecule. So I'm going to double my number of moles here. So I've actually got 2/5 of a mole of carbon atoms. But that's not the answer because they want to know how many carbon atoms that is. So now I'm going to have to multiply that by 6 times 10 to the 23 to get the number of carbon atoms present. And so 2/5 of 6, what's that, 1.2 or 2.4? It's going to be D, isn't it? So 1 is D. Slow start. Which of these has a molecular formula and empirical formula? So empirical formula is the simplest ratios of atoms in a molecule. The quick trick is I can't make this any simpler. It's only got 1 oxygen. I can't make that a smaller value than 1, integers only. So that must have the empirical formula and the molecular formula. Yes. The next one, well, isn't that clear that I could divide everything by 2? I could make that a 1. I could make that a 2. I could make that a 1. So no, that's not working. And the last one, what number goes into 5 and 12? That isn't 1. Okay, so also that one works. So 1 and 3, which is B, which is right. Second easiest question. Don't get too excited. 3. This question's wrong, but we'll do it anyway. This only works if it's at the same temperature and pressure, so you're not picking the right answer. You're picking the best answer here. So normally, if you've got the table, you could say 2 of those, 2 moles of that, is 7 moles of that, needs 4 of that, and 6 of that. So it's a ratio, or 20 of those. It's 70 of those, 40 of those, 60 of those. Nice. Now, we don't have moles, we have vols, we have volume. And you know what? If the temperature and the pressure is the same, you can still do that kind of that jig with the coefficients. So that's where we are. So what's the volume of ethane needed? So I need to know this value here. So what other numbers do I have? I've got 40 here, and I've got 140 there. 40 there, 140 there. Alrighty, are they trying to jerk me around with excess and limiting? Maybe, but I think we can short circuit this. So 4 is to 40 as 2 is to 20. So I need 20. So 3 is B. Yep. 4, mass spectroscopy. Never seen a mass spectrometer. What is the relative atomic mass? Alrighty, so I can see there's loads of the 24 and not a lot of anything else. So looking at my answers, I've got 24.0, I've got 24.3, I've got 24.9 and 25. Okay, so normally they'll give you a number that's beyond the range, like 23. That's obviously, you're never going to get that. 27, you're never going to get that. But here they haven't. 24 is wrong. That's just the most common isotope, but it's not the weighted average. 25 is wrong. All you've done is just picked the average of 24, 25, and 26. So you have to think it's probably going to be the average is going to be over there somewhere, isn't it? Closer to the 24. So I'm thinking 24.3. That one is B. Question 5. which is element is in group 13. So ionization energy is the energy required to remove an atom to remove an electron from a gaseous atom, standard temperature and pressure. So essentially group 13 has 3 valence electrons. And so that means there'll be 3 electrons that come off pretty easily, or they take about the same energy to remove. But then when you try and take off the 4th electron, well, you've gone in a main energy level. What the hell does that mean? It means that you're taking it off a shell closer to the nucleus. So it's going to be more attraction because the 4th electron is coming from a shell close to the nucleus, and there's less shielding electrons. So I'm looking for 3 electrons that take about the same energy to come off, and then the 4th one, it's just a lot harder. So that's about the same as that's about the same as that, and that, so that's wrong. That's at least 4 come off with about the same energy. That, and then all of a sudden this is 4 times harder. Okay, so that's the answer, I think. 3 electrons came off relatively straightforward, then the 4th one needs a lot more energy. Here, that's about there. And then all of a sudden, it's 10 times harder. So D, I think, would be group 1. What are we after? Group 13? So that's B, 5B. Is that right? Yeah. Trends going down group 1 and group 17. Well, easy trends for going down group 1 and group 17 is they have increasing atomic number, increasing mass number. Is that going to help? No. Okay. Melting points increase. Well, I know that francium's a liquid, almost certainly, and lithium's a solid. And I know that fluorine is a gas, and iodine, I've seen the crystals, that's a solid. So the melting points, no. Solid to liquid, gas to solid. So that doesn't work, does it? Boiling points, no, that's the same thing. Electronegativities increase as I go down. Well, fluorine is the most electronegative with 4. So as you go down, the electric negativities go down, they go down, they go down in every direction. So which trend going down? Electronegativities increase. No, that one's backwards. As you go down, they decrease. So it must be D. So 6D. Is that right? It is. Okay, well, let's try to explain that. Ionization energies decrease. So I think ionization energy is the ease with which you can pull off an electron. The ease with which you can pull off an electron. So which atom has an electron that is the loosest, the easiest one to come off? What hates electrons the most? Well, metals hate electrons. So it has to be a metal. It has to be one of these. Electrons love to be close to the nucleus. That's opposites attract, isn't it? Electrostatic attraction. So the negative electron is more stable when it's close to the positive nucleus. So francium is the biggest atom. So the electron is so far away, it barely feels the attraction of the nucleus. And there's so much shielding. The electron on francium is the loosest electron on the periodic table. You just look at it, the thing falls off. So it has a very low ionization energy, really easy to get that electron to fall off of francium because it's so far from the pull of the nucleus, lots of shielding. So that's going to be 6D. 7. Which oxide will dissolve in water? So last year I just gave my students exams without the questions to see if they could just intuit the answer just by looking at the answers. The average if you just guessed should be a 1, but the average if you kind of have some exam technique, some people got 3s. Some people got 3s in it. So I'm not even going to look at the question here. I see that I've got a non-metal, phosphorus. I've got a semi-metal. I've got a metal. And I've got a metal. So I bet the answer's phosphorus. Because semi-metals can go either way. What's the question? Which gives a solution which gives an acidic solution? So yes, it is phosphorus. If you look at the oxides, sulfur oxide makes acid rain, sulfuric acid. Nitrogen oxide makes nitric acid in acid rain. Chlorine oxide, some people are taking that to cure COVID. Oh my God. That's an acid. So non-metal oxides are acid. So I've never seen that oxide of phosphorus, but I bet it's an acid. Non-metal oxides are acid. So 7 is A. Is it? Yeah. Oh, that's the hardest question. Alrighty. 8I isn't really fair because in the previous syllabus, zinc was a transition metal. In the current syllabus, zinc is not a transition metal. Transition metals can have multiple oxidation states, so they can lose 2 electrons, 3 electrons, whatever. Zinc only has one oxidation state. Zinc is +2. So you never need to tell me that because I know zinc is +2. So why in the exams do they say zinc 2 sulfate? It can only be +2. You don't need to tell me. Who knows? So which of these is correct? Zinc is not a transition metal. That is correct. Is that enough? No. It just tells me 8. Okay. Ligands are Lewis bases. I have to think about that. So a ligand, I've got my water, and it ligands on like that, doesn't it? Dative covalent bond. All right then. So I can't remember the difference between a Lewis acid and a Lewis base. I'm just finishing a quick video. Just give me a minute. So I can remember this though. That's that funky thing with the boron and the nitrogen. I remember that lone pair bonds onto that. And I know that must be a base because it's ammonia. So then that must be a Lewis base. The Lewis base donates the electron pair. So that would mean ligands are Lewis bases. Yes, it's donating electron pair. So that's right. 1 and 2 are right. Is that enough? I don't know about 3. Paramagnetic. Well, good luck remembering that. I can only remember that because I did the experiment. I found that quite... So what have you got? You've got iron, nickel, cobalt. It's those 3 next to each other. Those are ferromagnetic. Yes. Okay. And then the next one was paramagnetic. Paramagnetic means that in the D block, in the 3D, there's at least one lone electron. At least one. And diamagnetic means there's no lone electrons in the D block. All right then, so manganese 2 chloride. Manganese, oh, this is taking more than a minute and a half. Manganese is 3D5. Okay, so let's have a think. Manganese 2 plus is 3D5. No, manganese is 3D5. So manganese is argon. Argon 4s2 3d5. But we're looking at manganese 2 plus. So that's going to lose those 2 electrons there. Okay, so it has 3d5. And if you remember 3d5, that's just, oh, there's so much information to process here. That's got, so what is that? That's paramagnetic. Because it has lone electrons in the d orbital. So it is paramagnetic. They're all correct. I think 8 all correct. So 8D, 8D. Okay, I'm going to stop the video here. I need to lie down. Okay, I'm back. Question 9. So what's got the shortest carbon to oxygen bond length? Okay, so what on earth is that? That's like an alcohol with the hydrogen ion removed. Then I have alcohol, carboxylic acid, it's ethanoic acid, and I've got the ethanoate ion. So that actually has a 1.5 bond between the carbon and the oxygens. It's resonating. So the shortest bond length is going to be the carbon-carbon double bond, which is this one, which is D. 9 is D. Double bonds are shorter than single bonds. Of course, the shortest one would be a triple bond, such as in carbon monoxide, which I thought they were going to go for, but they didn't. 10, which molecule is most polar? Okay, so it's all based on a tetrahedron. The central atom has 4 electron domains and no lone pairs. So it's a tetrahedron. So taking the first one, I've got 3 fluorines. 1, 2, 3, and then a hydrogen. That is pretty polar. The fluorines are going to drag the electrons all the way over to that side of the molecule. So I would think that's going to win. But let's look at the others. Oh, if I replace that with a fluorine, the molecule is non-polar because the bond dipoles cancel. This cancels out with this, cancels out with that, cancels out with that in 3D. So B is non-polar. What if I stuck a chlorine in there? Okay, if I put a chlorine in there, so chlorine has a high electronegativity like fluorine, so that means the fluorine won't be able to drag all those electrons up quite as far because the chlorine's going to hold them back a little. So that's wrong. And if I replace them all with chlorine, well, that's non-polar, isn't it? Bond dipoles cancel. So I think the answer's A. 10A, 10A. Nice. 11, most discriminating. I think the smarty pants got that. I have not seen that molecule before. So what I do is I add up the valence electrons. I've got 7 plus 4 times 7 plus 1. So that's going to be 35, 36. So it's divided by 2 because I want pairs. So 36 over 2 is 18. Bromine goes in the middle because it's first, BF4 minus. And I'm going to space the fluorines evenly around. Join them up. And I've got 14 more lines to go. 14 more electron pairs. I started with 18. I've accounted for 4. So 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 2 more to go. 17, 18. That's trigonal planar. No, so that's square planar, isn't it? Normally we do xenon tetrafluoride. So the electron domain geometry around the bromine. So the bromine has 1, 2, 3, 4, 5, 6 electron domains. But it wants another geometry, so it's going to be octahedral. 6 electron domains is octahedral, so it has to be A or C. The geometry, the molecular geometry around the Br, well, that's just the shape, so that's square planar. So that's going to be C. Okay, C. 11, C. Nice. 12, metallic bonding from strongest to weakest. All right, so the weakest metallic bond is francium. It's probably a liquid, no one's really sure. And so the further you get from francium, the stronger they are. So let's have a look. We want to do strongest first. So we have sodium, magnesium, rubidium, and potassium. Okay, so the strongest is going to be magnesium. That's the furthest away. And then we're going to have sodium, potassium, rubidium. So that's going to be D, 12D. Yep, 12D, just a regular pattern in the periodic table. 13, which statement is correct? What they're trying to see is if you understand that 13 is that ozone has not a double and a single like you might think. It actually has this 1.5 bond. It's resonating. I'm not going to join the lone pairs, never quite sure where to put them. And oxygen, that. So this bond is stronger. This bond is shorter. This bond needs more energy to break, which means it needs a higher frequency of electromagnetic radiation or a shorter wavelength. So what's that? Yeah, A. So 13 is A. Yep. 14, enthalpy of formation of ethanol. So that's making 1 mole of a substance from the elements in their standard state. It's the enthalpy of formation. So B must be wrong, it's making 2 moles. D must be wrong, it's making 2 moles. So A and C, I can't see the difference. Oh yeah, A must be wrong because ethanol is a liquid in its standard state, and it says it's a gas there, so it must be C. 14C, yep. 15. Okay, so in IB you need to know 2 exothermic reactions, combustion, burning stuff, and neutralization, acid and a base. So this looks like it's exothermic because delta H is negative and you're burning stuff. So that's going to be like that. Okay. So bond strengths. Now I remember that when you make bonds, it feels warm, gives off energy. I feel the heat. When you make bonds, it gives off energy. So there must be more energy involved in making bonds, heat, than breaking bonds, cold. So that must mean there's more energy released making the products. So the products have stronger bonds. So it's going to be A or B. Now, the activation energy. So the activation energy for the forward reaction is this. So I do think it's a one-way arrow. And the activation energy for the reverse reaction is that. So the forward is smaller than the reverse. So that's B. B, is that B? 15B. Okay. Next one, 16. Standard hydration enthalpy of this. Oh, it took me many years to find the shortcuts to do this. Okay, so it's a Hess cycle. All right then. So I've got sodium chloride, solid, and then you dilute it in infinite water. And then you can do the whole lattice energy thing. The whole lattice energy thing, which is making it to gaseous ions spaced infinitely apart. That turns to that, that turns to that. That's just... So the clockwise arrows equal the anti-clockwise arrows, but then you've got to know where to put those numbers. So let's have a look. The lattice energy is plus 760. So plus means you're breaking bonds, and I remember, so that's plus 760. The lattice energy is the energy change when you turn 1 mole of an ionic crystal into its gaseous ions. It's going to take lots of energy to do that, positive. The solution, I remember solution is the one that starts with the S that I'm left with. So these are the solutions here. So the heat of solution for sodium chloride is a +4. So this is going to be +4 this way. Solution with the solid. And now we've got turning the gas into the aqueous. I can't remember what that's called. That's called hydration. Okay. So the hydration for the chloride is -359, which leaves this as the unknown. So clockwise equals anti-clockwise. So I've got plus 760, these three here, plus X, plus minus 359. All of that equals the arrow going that way, which is plus 4. So to get X on its own, I've got X equals 4 minus 760 plus 359. Have I got that right? So plus 4. It's not 760, it's 790. Doesn't make any difference. There's only one minus 790. So B, is it B? 16B. It's like the first year I could do that without double checking my notes. I hate this next question. I don't know a quick way of doing it. Unless you just memorize it. Which reaction becomes more spontaneous as temperature increases? I think the universe likes it hot and messy, so I think that hot, so delta H, is negative. And messy is the entropy, so increasing entropy, so that's plus. So the universe likes it, it's spontaneous. When it's hot and messy. This is a minus. Temperature is always positive. Temperature is always positive. So it's in Kelvin. And so whatever numbers you put in for H, delta H, T and delta S, it's always going to be negative. It's always a spontaneous reaction. But that isn't the question. When is something always spontaneous? All right then, the universe doesn't like it when it's cold and tidy. There's no reaction that happens when it's cold, which is endothermic, and tidy, so that's reducing entropy. It's negative. This is always going to be a negative here, isn't it? It's always going to be negative here. So it doesn't matter what numbers you put in, delta G is always going to be plus. So that reaction never happens. So that isn't the question. It's the two edge cases. So what combinations have I not done? I've not done negative here and negative here. Negative and negative. All right then. So the way I think about it is as this gets more positive, bigger, 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 what does that do? Minus, minus is a plus. Oh God, so negative, minus, that's plus. So what's going to happen is the number's going to become more and more positive for delta G. So as temperature increases, delta G gets bigger and bigger. So we want one that becomes more spontaneous as temperature increases. So it's the last one. So what's the last combination? Would be plus and plus. So let me think what happens with the temperature. It gets bigger and bigger and bigger. So as it gets bigger and bigger and bigger, it's going to get more and more negative. Isn't that the one? Oh man, more and more negative, more and more spontaneous. So that's the last one. Still not answered it. So I need something that's endothermic and with increasing entropy. Endothermic and increasing entropy. So endothermic is bond breaking. So let's find the bond breaking one. First one is bond breaking. So it could be that. Could be that. The second one, there's some bond making, some bond breaking. I don't know. The third one is reversive combustion. It's reverse combustion, whatever that is. So instead of getting hot, it's going to get cold. It's going to be endothermic. Oh yeah, so we want endothermic, don't we? We want the endothermic. And the last one, I'm turning two things into one, so almost certainly I'm bonding them together in a way that's going to be exothermic. So that's wrong. So I've got A, B, and C. It's got dark outside trying to solve this. So entropy has to increase. That means in IB that you're making more gas than you started with. Am I making more gas than I started with on the first one? Yes. Am I making more gas than I started with in the second one? No. So that's out. For the third one, am I making more gas? I've got 7 on that side and 6 on that side. No. So it's A, 17A. There must be an easier way to do it because that wasn't the most discriminating or the most difficult. So if you know, help me out, put it in the comments, or maybe just memorize it. 18 is the easiest. Follow the rate of reaction. A pH meter, certainly. I can see acid there, so a pH meter is going to work. Correct. A gas syringe, am I making gas? There's no gas, so the gas syringe isn't going to work. And the last one, a colorimeter. Is anything going to be changing colour here? Yeah, iodine's purple. You need to know that. Purpley grey. It's purple in alcohol, so it's kind of purpley grey in water. Anyway, it's got a colour, and this must have a different colour. So yeah, colour will work as well. So it's 1 and 3, which is B, 18B. Nice. 19. What doesn't increase the rate of reaction? So rate of reaction's collision theory is to do with the rate of collisions of the reactants, the geometry of those collisions, and the energy of those collisions if they're greater than or equal to activation energy. So which does not increase the rate of reaction? Making it more lumpy doesn't increase the rate of reaction. So the answer is A. 19A. Yeah. 20, the units for the rate constant. Okay, question 20 from a strange angle. Rate is measured in change in concentration over change in time. So I'm going to use the old molar per second there. The units for the rate constant we don't know, but I know that concentration is measured in molar, and I know that this concentration is measured in molar squared. So I've got to get the units the same on both sides. That's what an equation means. Oh man. That's what an equation means. So I'm going to get rid of that m squared by putting m squared underneath. And I need that second to work there. Okay, the units are the same on both sides now. This is gone, and it's all equal. All right then. So what are the units now for this k? Well, I've got like an s at the bottom and an m squared at the bottom. So to convert that, seconds to the minus 1. And that is C. 21. Oof. Rate constant versus temperature. So you know the only thing that affects the rate constant is temperature. The hotter it is, the faster it goes. So if it's, what are the axes here? If it's rate constant and temperature, the hotter it is, the faster it goes. The Arrhenius equation, that's pretty complicated. Is it a simple relationship? Double T, double K. No, it isn't. It's this ridiculously complicated relationship. So it has to point upwards, and it has to not be a straight, simple line. So that's C. A and C both go up, but C's the more complicated one. It's C. Is it 21C? 22, equilibrium. The Chatelier's principle for a system in equilibrium. When it's stressed, it shifts to oppose the stress. This is endothermic, so I like to think it's kind of cold. There's a snowman there. Cat up for his nose. Lovely. And so over here, it's exothermic. This little devil, it's hot over there. Right. So if I increase the temperature, it's going to favour the endothermic side. So it's going to go shift to that side. Now, since Ka is the concentration of the products over the reactants, if it shifts to more products, Ka is going to go up. So if I increase the temperature, it's going to shift right, and Kc is going to increase. That's D, 22D. The only thing that you know that changes Kc is temperature and a catalyst. 23. Which statement is true for a spontaneous reaction? I haven't really seen this one before. So delta G theta, the standard Gibbs free energy. If it's negative, it's spontaneous. And what's going on with the equilibrium constant here? Okay, so let me think of a super spontaneous. Let me think of a reaction I know that happens. So I know that hydrogen reacts with oxygen, and it's really, really spontaneous in the sense that once you light it up, it will just run away. So this is very, very heavily over to this side. It's like 99.9% this side. So what's my value for Ka going to be? If there's loads and loads of product, it's going to be big over small. So Ka is going to be big. So it's A, 23A. Not really sure what I did there, but I got the right answer. 24, the second hardest. Oxides contribute to acid deposition. I asked this a few years ago. Sulfur oxides, yes. Nitrogen dioxide, yes. I don't think they accept NOx. Reflection of myself there, looking at myself. That's very Inception. NOx includes NO, which isn't an acidic gas, so just stick with NO2. Carbon dioxide is acidic, but it is not the one that we are looking for because it doesn't go to acid deposition. That tends to be those two gases. Carbon dioxide is kind of I don't think it sticks onto dust like those other two do. Anyway, so that's 1 and 2, that's A. 24 is A. That's just a little quirk of the IB there. 25, I'm not even going to look at the question. What's the answer? I've got a strong acid, a weak acid, I've got another weak acid, and I've got, that's a salt, so it's going to be an acidic salt. I don't know, so maybe it's hydrochloric acid. What's the question? Which of these acids has the weakest conjugate base? Okay, so the strong acid has a weak conjugate base, and they want the weakest conjugate base. So the strong acid is HCl, which is A. You need to know 3 strong acids: hydrochloric, nitric, sulfuric. There are others. 26. What's a Lewis acid but not a Bronsted-Lowry acid? Okay, Bronsted-Lowry acids give away an H+. So it's got to be a Lewis but not a Bronsted-Lowry acid. So this one's wrong. That's a Bronsted-Lowry acid. That can give away an H+. Not a Bronsted-Lowry acid. This one's wrong because it could give away an H+, I suppose, couldn't it? It's got an H+ kind of tagged on the end. So I'm left with copper and copper 2+. So a Lewis acid, I can never remember the definition. So what I do is I go back to this. I draw out boron trihydride. And I go back to ammonia. And I remember that lone pair there forms a dative covalent bond. I'm getting deja vu. Did I do this yesterday? There we go. And I know that's a base because it's ammonia. So that's a Lewis base. So the Lewis base donates the electron pair. So a Lewis acid must receive an electron pair. Well, which of these is going to receive an electron pair? Probably the one that's positive, isn't it? Because positives receive, and it's going to be a ligandy thing, isn't it? Okay. So I think the answer for that is 26A. 26A. Yes. 27. What's the pH of that? Well, I like to draw this grid. I've got pH here. POH there, hydroxide here, H+ there, and just fill it in unthinkingly and blindly. So this is 10 to the minus 4, which means it's POH4, which means that must be 10, because they both got to equal 14, standard temperature pressure. And then this is going to be 10 to the minus 10, because when you multiply them together, you get 10 to the minus 14. What's the question? pH of ammonia. So the pH of ammonia is 10. So 27 is C. C. Yep. 28. Oxidation states. So all elements have an oxidation state of 0. Fluorine always has an oxidation state of -1, which is tricky because now oxygen's +2. And peroxide, oxygen is always -2 in a compound. That's what we thought, but not for peroxide, it's -1. So that fluorine is -1. That's like the base rule. No, not the base rule. It's like the rule that cannot be broken. Okay, what have I got? 0, +2, -1. 0, +2, -1, C. 28C. Yep. 29. Oh, electrochemistry. Let's hope this is easy. What am I trying to do? Okay. So electron direction. Iron is a stronger reducing agent than silver. So I think a reducing agent is itself oxidized. Reducing agent is self-oxidized. Oxidation is loss of electrons. Okay, so iron wants to lose the electrons. So the electrons are being vomited off the iron going that way. Is that enough? Electron flow from right to left. So that gives me A or D? Next one. And so since iron's giving off the electrons, it's the negative electrode, where the electrons come from. So the negative electrode is iron, so that's D, isn't it? 29D. Yeah, 29D. 30. All right then, so if I want to lay down lots of copper, more current is more copper. So it's going to be that one or that one. Now for every 2 electrons, I get 1 copper atom here laid down on my electrolysis. But for every 1 electron, I get copper laid down. Oh, so that's better value for money, isn't it? So 5 amps and copper 1+, that's going to give me the most. Was that the question? The most. So 30 is D. 31. I don't know the answer to this one. I just did it by knowing what wasn't the answer, and it just popped out. So I want a silver plate, a zinc spoon. So that's electrolysis. I've got my positive electrode, my negative electrode. If I put the zinc spoon on here, and then I want to coat it in silver. So I probably want to have silver ions here, and then those silver ions will go over to the negative zinc spoon, pick up electrons, turn to silver. The negative electrode is made of silver. No, the negative electrode has the spoon on it. So A's wrong. The positive electrode is a zinc spoon. No. The negative electrode is the zinc spoon, so it attracts the silver ions. The positive electrode is made of silver. I don't know. Is it? Does that matter? If that was silver, would that help? The electrolyte is zinc sulfate. No, if I had zinc sulfate in here, I would zinc plate my zinc spoon. So by a process of elimination, it is C. I'm not quite sure why. I suppose the silver turns to silver ions in that funky electrolysis. So 31 is C. 32, name that molecule. So we tell you to try and get the lowest numbers with the branches. It's not quite true. You've got to try and get the alkene with the lowest number. That's the truth. There are 72 IUPAC rules last time I checked, and you probably do maybe 12 of them. So I've got 1, 2, 3, 4, 5, 6 carbons in the longest chain. So that's going to be hex. I see it's a double bond. It's going to be ene. The double bond is between the second and the third carbon. Choose the lowest number, hex 2-ene. And I've got branches on the 2, 3, and 5. So 2, 3, 5, trimethyl, hex 2-ene. Great. 33. What will decolorize bromine water in the dark? A test for a carbon-carbon double bond. Don't say a test for a double bond. A test for a carbon-carbon double bond is it decolorizes bromine in the dark. So it's a test for carbon-carbon double bond. I only see 1 carbon-carbon double bond there. So that's going to be C, 33C. If you shot it with a light, then the bromine might undergo homolytic fission and then do some funky stuff. What can be oxidized? That's a bit of SL. So you've got ethanol, ethanal, ethanoic acid. So they want a carboxylic acid, so it's ethanol, ethanal, ethanoic acid. And that was primary alcohols, wasn't it? Primary alcohols did that. So what's a primary? The propanol is the answer. So why is that a primary alcohol? Find the OH, find the carbon attached to it. How many carbons directly attached to that? Just 1, it's primary. Propan-2-ol is a secondary alcohol, so that would make propanone. 2-methyl-propan-2-ol is tertiary, doesn't oxidize with that. And propanone doesn't oxidize either. What's the electrophile? Electrophiles love electrons, so it's the positive thing. there are two positive things. So it could be NO2 plus or NH4 plus. It's actually that one, the nitronium ion. You have to learn that. But it looks a bit like nitrate, doesn't it? Nitrate's NO3, that's probably your closest one. And it's made from concentrated nitric acid and sulfuric acid. 36, butanene. What's the major product? So this is a Markovnikov. I think hydrogen likes to go with its brothers. So I've got butanene. I won't draw in all the hydrogens, I'll just put lines. That will cost you a point in the real IB. And I've got HBr. So like all addition reactions, one thing, this will split in half. And one thing goes on one side of the double bond, the other on the other side. So I've got a choice. Where am I going to put the hydrogen? Well, it's got to go with its brothers. It wants to go with the other hydrogens. So when this double bond splits, the hydrogen's going to go there to be with its other two. If it went here, it's not with its brothers. There's only just one. It wants to go with the other hydrogens. So what's the name for that? 2-bromobutane. C, 36C. This does feel an easier exam than regular. Most discriminating. So there are two most discriminating questions. The one that tells us smarty pants from regular humans. So I'm looking for a chiral carbon. Is it enantiomer? Chiral carbon. So that's a carbon with 4 different groups attached. So not that one, not that one. This one's tempting. That's got a hydrogen, an alcohol, and 2 ethyl groups. No, not that. I'm looking for something where it looks like they've just tried to force it to be 4 different groups to make it look weird. And so my sixth sense says that this looks weird. So this carbon here has a methyl, a hydrogen, a bromine, and a propyl. That's it. So 37D, pretty discriminating. 38. What's the percentage uncertainty? Well, you have to add up the individual percentage uncertainties. So 0.2 over 20 times 100. Is that 1%? 2 would be 10. So that's 1%. And this is 1 over 10 times 100, which is 10%. This has no uncertainty, so don't worry about it. So I'm uncertain by 11%. Now, following the IB rules, you can't have 2 sig figs your uncertainty. You're uncertain about it. How the hell will you give me 2 numbers? So it should be 10. 10 is not an answer. Don't choose the right answer, choose the best answer, which is 11. So 38 is C. 39, index of hydrogen deficiency. So every carbon-carbon double bond is worth 1. Carbon-carbon triple bond is worth 2 points. And every ring is worth 1 point. I see one ring. And secretly hidden in here, is there a... that isn't there. So that's gone, my mistake. So that's the correct answer. There's just one ring, so the answer's 1. I miswrote it down. I thought that was benzene. So that would have been 4. But it's just 1. So that's 39B and 40 H1NMR. Ooh. We have to do the splitting. I have to teach that tomorrow. So I've got 4 peaks, so 4 hydrogen environments. Let's see if any of these have 4 hydrogen environments. It's that one. So this has 1, 2, 3, 4, 5 hydrogen environments. That's wrong. This has 1, 2, 3, 4. That has 4. Could be that one. Next up, there's 1, 2, 3. That's wrong. And this has 1, 2, 3, 4, 5. So it's B, and we are